Thank you very much.
By the way, he got his PhD in 2011.
Exactly. Thank you very much. So it's a huge pleasure to be here and to see again people face to face, so many friends and familiar faces, and even to know the students which I have been teaching in the last couple of years, which I just saw on the screen. So it's a really great pleasure to be here. So after my PhD, I joined the Portuguese National Laboratory for Civil Engineering in 2013. And that's actually when I started working on experimental works. So before I was mainly doing numerical activities. So I've been involved in many different activities, probably too many in the last years. But I was asked to give a talk on the experimental activity, and so that is what I'm doing today. Going into the field of the reinforced concrete frames with masonry infills. And as we saw from the previous presentation, experimental activity is really important to get our numerical models better. So I will talk a little bit about the motivation, the modeling, and the experimental testing, not by disorder. So I will mix a little bit the different aspects. So we all know about the influence of masonry infill panels in the building response, be it by changing the strength, the stiffness, the failure mechanism that we get. So we may get short column effects, soft story mechanisms which we were not expecting. We have in-plane damage in the infills, but we can also have significant out-of-plane damage, which can cause fatalities, as we have seen in recent earthquakes. Looking at this issue of the out-of-plane collapses, for instance, you have here a plot of different authors which have done experimental testing, and you see how much is the reduction of the out-of-plane capacity when you impose an initial in-plane drift. And you see, well, first of all, you see a scatter of results, also because different types of masonry units are used and different types of tests are conducted. But you see immediately the influence that one has on the other. In terms of experimental testing, what can we reproduce in terms of this behavior and achieve in experimental testing? So we are looking to assess what is the response in terms of collapse mechanisms, in terms of ductility and ultimate drift capacity, in terms of differences in energy dissipation, the interaction between the frame and the masonry infills, and I will also be showing some examples of retrofitting solutions and strengthening solutions for the masonry infills. Now, looking at a first example of experimental test, we have here a scale, a 1 to 1.5 scale mock-up that we have tested at the next shaking table, which has, it's a reinforced concrete frame with double leaf masonry infills to avoid thermal bridges, and so this structure has been subjected to a number of stages of seismic action, of different and increasing seismic intensity. And if we look at the video of the final test which was done on this structure, we see the failure, first of all, of the outer leaf of the masonry infills, and when that happens and the inner leaf of the masonry infills also starts to get serious damage, the reinforced concrete structure immediately collapses after that. So you have a significant change in stiffness, in strength, and you have a full collapse of the structure. And so we have this outer leaf collapse, and then the inner leaf collapse, and the complete failure of the building. So in this particular specimen, or not that one, a similar specimen, we were doing some reinforcement using a wire mesh reinforcement in a reinforced mortar coating, which was anchored to the reinforced concrete elements and also to the masonry units. And so this structure was constructed, and we did the same type of test, so the same stages, and now we are looking at the response of this reinforced specimen for the same stage of response, which is a much better response, of course. And you see, well, you see several wires in there. They are not cracks. There are some cracks, but you see several wires which are for the optical transducers. But so the response was pretty much improved by having this reinforced solution. But when you go and you look into the details of the response of this retrofitted or strengthened building, you see that you still have considerable cracking of the mortar coating, and when you remove this mortar coating, you start and you see that, for instance, at the joints you have significant cracking. You also have some cracking at the connection when you have the crack at the infill and when it reaches the column, and so you have, even though the response was much better, you still have significant damage in several elements of your structure. So this reinforced masonry specimen has presented a clearly superior seismic behavior, but nevertheless we have a failure mechanism which is under development, is still potentially a fragile one and an undesirable one. But the out-of-plane collapse of the infill walls was successfully prevented. Now, looking at the modeling of the infill masonry walls, just giving an overview of the type of modeling, so we can go to micro models and go into the details if we have enough parameters, if we have enough data to calibrate and to validate the parameters that we use on the model. But typically people are using macro models to model the global response of a reinforced concrete frame with infills, which allows to capture well the global response of the structure. So for this type of macro models with single or double or triple struts, there have been different proposals throughout the years. Ever since the 60s, and it's still a very active field. And more recently, there have been a number of proposals which are looking into the out-of-plane response and not just the behavior, the contribution to the in-plane response. And so you have a number of proposals since in the last 10, 15 years, which are looking at this out-of-plane response, typically introducing some mass at the center of the panel and including the nonlinear response for the out-of-plane to try to capture this nonlinear behavior. So some of them include the interaction between the in-plane damage and the out-of-plane capacity, and vice versa. Where you have here, so an example, for instance, of the Furtado model, where you have this losange interaction diagram between the two of them. So in terms of the parameters for the in-plane, so we have several expressions for the stiffness, the strength, depending on the type of failure that you obtained for the particular infill, and then you also have to define the envelope and the cyclic behavior, and there are a number of proposals to do so. Of course, there is all of these proposals will lead to different results, and if we look, for instance, at the issue of the opening, so what happens to this single strut model when we have a masonry infill with openings, you see the scatter that you have in the different proposals for the reduction in the stiffness and strength capacity from that different authors are proposing, depending on the size or the relative area of the openings. Well, anyway, the models that do exist, they are able to replicate well the experimental results. So we have here a few examples. taken from several different authors. So the test from Cacalet is for the bare frame and for the infilled frame, the tests from Pires, the test from Morandi et al. Here in Pavia. And so you have a number of tools that you can use to make this type of modeling, and if they are well calibrated and validated, they produce a very good result at least for the in-plane response. They are working very well. Now, looking again at the experimental testing of masonry infilled reinforced concrete frames. So for obvious reasons of economy and test repeatability, it's interesting to do substructuring tests where we have to be aware of the boundary conditions and of the seismic input. But so the state of the art is, since the 90s up to now, is by applying it. So, and in terms of having both the in-plane and the out-of-plane response, you can have this type of setup where you apply in-plane loading and you apply through airbags or some other type of device the out-of-plane forces. We have an initial attempt here by Komaranemni in 2009 to use a shake table to apply the out-of-plane action also on the specimen. And other authors using, instead of the airbags, actuators to apply this out-of-plane forces. So at LNEC we have come up with an interesting setup which we call TIM. So it's the testing device and methodology for innovative masonry walls building solutions. So this was actually in the first year that I was working at LNEC that we were doing the initial experiments with this setup. And so the idea is that so our shake table is a particular one because we have 3 reaction walls around it, and so we are able to do different types of setup. And so the idea here was to use simultaneously the shake table to impose the in-plane drift and at the same time the out-of-plane action, and one of the reaction walls to actually be able to impose the drift between the two floors of the element. So we have this very large steel structure that you see, the red steel structure, which is very stiff in the transverse direction. So the idea is that it transmits the movement, the out-of-plane motion of the shake table to the upper beam of the reinforced concrete frame, such that the reinforced concrete frame moves as a rigid body, and so you have the infill wall only vibrating or having the freedom to vibrate relatively to the reinforced concrete frame. Okay, so we impose the in-plane drift to this by having a strut, a fixed strut to the reaction wall, and the motion of the shake table in the in-plane direction, and then we impose the out-of-plane motion, which consists of a rigid body vibration of the reinforced concrete frame, and then the relative vibration of the infill wall. So just taking a look at the device, a small animation just to look at different details. So we have rollers at the top beam to allow that the shake table and this large steel structure moves along the longitudinal direction of the beam, while still being able to impose the out-of-plane drift. Okay, and so the idea that for the seismic input that we are imposing to our model is to take the expected response or the expected input that we have at the given floor of a building, and so we define the in-plane and out-of-plane dynamic actions for this inter-story action and response. So, for instance, for the initial tests, these are the signals that we were considering, and so we were doing these tests that they were still from the series project. with NTUA, was the leader of the user group which was using the facility at that point. So we had this reinforced concrete frame, and we tested both the unreinforced and reinforced solution with this type of bed joint reinforcement placed every 2 layers of masonry units in the infill. So on the very first test that we did, and I will talk to you about in this slide and in another one, I will talk to you about what goes wrong in experimental activity. So many times things go wrong, they are not going as we expect. And so for this very initial test, we realized that the in-plane elements the in-plane elements which were connected to the reaction wall and so on, they were having too much flexibility or having some slack, and so the in-plane action was not able to be imposed. And so basically this initial test was a test where we have the response of the infill just for the out-of-plane vibration. Okay, and so we reach this type of mechanism where you have an horizontal crack and a vertical crack for the out-of-plane only seismic action. But going to the first actual test, which was successful, so with in-plane damage, so we started to have the collapse mechanism formation at 34% of the reference input. This mechanism was composed of horizontal cracks at about 1/3 and 2/3 of the infill height, and then diagonal ramifications towards the corners, and then after some testing with posterior destruction of the upper row bricks due to transverse motion. In terms of the out-of-plane fundamental frequency that we were measuring, we went from the beginning of test to the end from 20 yards to 3 yards, so a huge decrease of the stiffness. And so you see here the damage evolution throughout the different stages of test. Here an example of the difference between the cyclic response in plane for two of the stages, and the video of the test when we were doing the final stage of testing, where you already see that the out-of-plane frequency of vibration is pretty much reduced. You see the sliding at the 2 horizontal cracks, and you see some damage which is occurring at the upper bricks on the right corner of the figure as we impose the seismic action. So now, if we move on to the reinforced masonry test, so we had an in-plane collapse mechanism, which basically initiated at the same stage of testing. So this is the reinforced masonry where we have those bed joint reinforcements. But here the initial mechanism was composed of 2 main diagonal cracks, so not the horizontal cracks anymore. And again, with a posterior development of groups of diagonal cracks so for this particular solution where we had this bed joint reinforcement, we ended up having a mesh of cracks all around the infill, as you will see. So the damage evolution is going like this until the very end, where you see on this figure on the right, where you already have pieces which are completely inclined, but they are not falling out of the model because of the bed joint reinforcement. And so if you look at some videos of test results, so the upper left is a lower stage, then the lower left is an intermediate stage, and on the right you have the final stage, which is actually more advanced now in the video, but you will see the others moving soon. Okay, and so you see, for instance, at the very final stage, that the cracks, they are very wide. You have a huge damage on the infill. but still it is not collapsing in the out of plane direction because of the bed joint reinforcement. Okay, so I guess you got the picture. So looking at another test campaign which was done with a national research project, we were again looking at this issue with different dimensions of the reinforced concrete frame and of the infill, and looking at a JFRP mesh reinforcement in the coating of the infill. So again, a single leaf masonry, again traditional horizontal hollow brick units. These are smaller than the ones of the previous tests. They have a smaller width, but these are the typical bricks which are used in Portugal and in many other places. So again, the seismic input is coming out of a numerical model. We have a number of different test stages, and the type of response that we get for the unreinforced specimen for the different test stages is like this in terms of the in-plane response, so a significant degradation of the in-plane stiffness and also a little bit of the capacity. And in terms of the failure mechanism, you have two main diagonal cracks which have formed, and then they join the horizontal beam at the bottom, and they go horizontally up to the columns. Now, for the reinforced specimen, we started, okay, let's try to innovate here a little bit, and so let's do some different control. So looking towards going into hybrid simulation tests with this type of structures, which would be very interesting to achieve. So we were trying to control the motion of the shake table, not by using the normal control that we have at the shake table, but by using directly the deformation of the specimen. Okay, so this is a very rigid specimen, and so using this displacement at the initial stages is a very difficult task. Well, particularly if you have a wrong sign in your control system. So it's an in-house control system, and so sometimes you get errors which turns into a little bit of a nightmare when you look at your model and you see what has happened. So basically, the feedback to the control system ended up imposing the full motion of the shake table to the specimen, and so we imposed 20 centimeters drift between the two beams of the specimen, and so we had this collapse of the infill with actually, well, you can always take some good out of it. So you have a very nice plastic hinge formation at the bottom of the column there that you see, with a nice spacing of the cracks. But so there were two, in one of the previous pictures, there were two very sad people coming out of the control room and looking at the specimen. So. But anyway, this gives us some results which are interesting. So this green curve that you see in there is basically the in-plane capacity of that infill structure, and you are comparing it here with the brownish curves are the ones which were made when we had both the in-plane and the out-of-plane seismic action on the specimen, and you see the effect of having both directions of seismic action on the capacity of this type of specimen. So one of them was the unreinforced, the other one was the reinforced, but that doesn't really play a role here, because for the in-plane capacity, the mesh reinforcement is not giving any particular additional strength to the model, as we will see in the successful reinforced masonry or reinforced specimen test. So looking at take two of these tests, so we let's see if it goes. Okay, so we have this type of cyclic response throughout the stages. You don't have here the previous one for the unreinforced, but in terms of the capacity, of the strength capacity, it's very similar. So the mesh reinforcement is not giving additional strength, but it is sustaining the out-of-plane collapse for a long time and up to much larger drifts than the previous one. And again, if we compare this cyclic response with the pushover, the in-plane pushover of the reinforced concrete frame, you see the effect of the in-plane and out-of-plane simultaneous input on the response of the masonry infill. So in terms of the damage, you see here the strengthened specimen was presenting a more distributed cracking, much more distributed cracking. In terms of the fundamental frequency on the out-of-plane, we were again going from a large frequency of 9 Hz to around 2.6 Hz at the end, and the reinforce included in the coating was successful in preventing the full out-of-plane collapse. So in terms of the final comments, so there are several promising modeling developments for practical use that one can adopt. And actually this type of modeling, the single strut modeling, is foreseen for the next generation of Eurocode 8. But for sure we need additional testing. And these tests that I was showing and this test setup, they are beyond the current state of the art in terms of experimental testing. And it was actually, by the time it was awarded an innovation award back in Portugal. But of course that things keep on developing, and now we have this fabulous 9D lab in our center, which is a new dimension, so it's the 9D dimension. And so I think we have a brilliant future ahead for this type of testing with this new type of facilities. So thank you very much for your attention.
Thank you very much, Antonio, for your presentation. Since we are only slightly behind schedule, I will keep my questions for private conversations with you. There is still time, however, for some questions from the audience.
Sure.
Paolo.
Thank you, Antonio, for your presentation. I would like to ask you a question. Many of us are here involved in the drafting of Eurocode 8, and some of us also, of course, in the part of infills. Given your experience, both numerical and experimental, even this new type of experiments, considering the simultaneous effect of in-plane and out-of-plane, what do you think? Which hints can you give to the draft of the Eurocode 8 for infills regarding the improvement of this draft? We need to finalize the draft in a few years' time from now, so we need to push and focus on a few aspects. What do you think are the main aspects to improve in the actual draft of Eurocode 8 according to you? Thank you.
Well, that's not an easy question. For sure. So, in my opinion, it is becoming more and more difficult to do the design according to the Eurocodes, and what is being asked for this new generation in terms of the infills will not make things easier, for sure. I think we still need a lot of data, a lot of experimental data to have confidence in the models that we are using. But as you can see, I mean, these type of models, they are really able to capture the differences in response in terms of stiffness, in terms of strength. So they are really helpful in trying to understand the real behavior of a reinforced concrete frame with infills. But I don't have really an answer to give you. I mean, it's something that for sure will still inspire a lot of debates within the SCA, it's for sure.
Yes. And second, very brief question. Do you think that it's possible to have a protocol, a loading protocol, in the case of simultaneous in-plane, out-of-plane response on shaking table, which is able some way to help to find, you know, new criteria for the in-plane and out-of-plane response? Because of course in the case where you use a sort of numerical analysis, you are actually experiment a specific case, a specific motion with a specific structure. It's very useful to evaluate the performance of the infill and eventually also the strengthening techniques performance. But in terms of developing or verifying strength criteria, verification criteria for designers, do you think that there would be some protocol for such tests that could help us to find, you know, this criteria, verify them?
Yeah, well, for sure, this type of having this type of criteria would be helpful also to be able to make comparisons between the different testing. Although the different testing facilities, the tests that they are doing, they are also quite different between themselves. But yeah, so and also connecting to the design, to the Eurocodes, so it should be somehow connected to the peak floor acceleration spectra that we are considering, and so using those tools, it would be very nice to come up with this type of protocol. But I think we are still a bit far from that.
Thank you very much.
You're welcome.
Okay, so I think that now we can close the session. If there are more questions for the speakers, we have the coffee break, the lunch breaks, and I simply would like to ask you to join me with a final applause to all the three speakers. They have given excellent presentations of outstanding research, and so I think this was a very interesting session. And please try to come back on time for the next session, which is scheduled to start at 11:30. Yes, so we don't accumulate too much delay. Again, an applause to